Space is not the silent void it appears to be. Between the stars, vast and shadowy clouds of gas and dust drift in the darkness. These are interstellar molecular clouds, the cosmic nurseries where new stars and planets are born. Yet from within these quiet cradles, astronomers sometimes catch whispers, strange and fleeting signals that defy all explanation. These are not the sounds of creation, but puzzles that challenge our understanding of the universe itself. By the end of this journey, you will know 25 of the most baffling signals ever detected from these clouds, each a mystery waiting to be solved. We will encounter a signal so powerful it was scribbled WOW and pulses that echo back like a cosmic boomerang. What do you think it means when the universe sends a signal we cannot understand? The first and perhaps most famous of these cosmic enigmas is the WOW signal. On a quiet August night in 1977, a radio telescope in Ohio picked up a burst of radio waves so intense, so perfectly tuned, that the astronomer who found it circled the printout and wrote a single word in the margin: "Wow." It lasted 72 seconds, came from a specific point in the constellation Sagittarius, and then vanished, never to be heard again. For decades, it stood alone, a tantalizing one-off event. But recent research has woven a new layer of intrigue into its story. The precise direction of that powerful signal points not into empty space, but toward a region rich with interstellar molecular clouds. These are not just any clouds, but complex structures of gas and dust that could, in theory, focus or amplify radio waves from a source far beyond them, like a cosmic lens. This connection deepens the mystery profoundly. If the signal originated from within the cloud itself, what natural process inside a stellar nursery could produce such a brief, powerful, and seemingly artificial burst? If it came from something far behind the cloud, why has that source never repeated? The cloud does not give us an answer, it merely provides a stage, a dark and dusty curtain from behind which the universe delivered its most famous unanswered message. The WOW signal was a solitary shout into the void, but the universe soon proved it could send more than just a one-time message. Years later, in 2007, astronomers sifting through old data from a radio telescope in Australia found something that would reshape the entire field. It was a blast of radio waves so incredibly powerful, it lasted just 5 milliseconds but packed more energy than our sun emits in an entire month. This was the Lorimer burst, the very first recognized fast radio burst. Its discovery confirmed that the cosmos was capable of these brief, cataclysmic explosions of radio light, events so immense they must originate from billions of light years away. The mystery of the Lorimer burst and the many FRBs discovered since is not just their power, but their journey. To reach us from such unimaginable distances, their signals must travel through the vast, lonely stretches between galaxies and, crucially, through the hearts of the galaxies they come from. This is where molecular clouds re-enter the story. Picture a lighthouse beam cutting through a dense, rolling fog. The light scatters, its path distorted, its clarity lost. Theorists now believe that some repeating FRBs, especially those with strange, twisted signatures, might be generated within or directly behind the thick molecular clouds in their host galaxies. These immense clouds act like that cosmic fog, scattering the radio waves in unique and complex ways. By studying the subtle fingerprints of this scattering left on the signal, astronomers are trying to do the impossible, to peer through that dusty veil and decode not just the signal, but the turbulent environment it passed through. Each burst becomes a probe, its distortions a map of the invisible structures that birthed it. While fast radio bursts travel across galaxies, some of the strangest signals come from much closer to home, from within our own cosmic neighborhood. Deep within the constellation Taurus, a sprawling, dark mass of gas and dust known as the Taurus Molecular Cloud drifts silently. It is one of the closest stellar nurseries to Earth, a place we have studied for decades. Yet from its shadowy heart, astronomers once picked up a signal that behaved like nothing else. It was not a simple burst, but an echo, a radio pulse that seemed to travel out, hit something, and bounce straight back. This was the boomerang echo. The timing was all wrong. Based on the known distance to the cloud, any echo from a simple reflection should have taken years to return. This echo came back in mere days. It was as if you shouted into a canyon and heard your own voice return almost instantly from a wall that was supposed to be miles away. This bizarre timing defied every conventional explanation. A simple dust cloud could not account for it. The leading theory points to something far more exotic hidden within the cloud, a hyper-dense, compact object like a black hole or a neutron star surrounded by a swirling, magnetized disk of material. The idea is that the original radio pulse did not simply bounce off this object, but was captured by its powerful magnetic field, stored for a brief, chaotic moment in a whirlpool of energy, and then violently spat back out in our direction. This process would warp the signal, imprinting it with the unique fingerprint of that hidden object's ferocious environment. The Taurus cloud, a place we thought we knew, may be concealing a cosmic predator in its midst, one that catches our signals and throws them right back at us. What else might be hiding in the dark nurseries of the stars, waiting to send our own curiosity echoing back in forms we cannot yet recognize? That boomerang echo hints at hidden engines of chaos within the clouds, and sometimes the clouds themselves seem to turn their hidden energy into a focused beam of light. This brings us to the strange case of the cosmic lasers, or more accurately, masers. In the constellation Cassiopeia, a brilliant and turbulent stellar factory known as W30H blazes with the light of newborn massive stars. Within its swirling gases, astronomers observe something extraordinary: natural masers. A maser works like a laser, but instead of visible light, it amplifies microwave or radio waves. Specific molecules like methanol act as the fuel. When they are energized by the intense radiation from young stars, they can emit incredibly bright, coherent beams of radio light, natural beacons shining from the nursery. But in W30H, the methanol masers do not just shine steadily, they flare and flicker with a violence that defies simple explanation. Their brightness can change dramatically over just a few weeks, a heartbeat in cosmic time. Even stranger, these fluctuations sometimes travel in waves across the cloud, as if an invisible ripple of energy is passing through, switching the masers on and off in a sequence. So what cosmic switch is being flipped? The raw power of the young stars is not enough to explain such rapid and patterned volatility. Theorists are forced to consider far more dynamic events, perhaps violent collisions between dense clumps of gas within the cloud, or sudden eruptions of material from the protostars themselves slamming into the surrounding methanol. Some even speculate about the influence of hidden, powerful magnetic fields, twisting and snapping like rubber bands, releasing torrents of energy that surge through the cloud. These masers are not just signals, they are the frantic gauges on a cosmic pressure cooker, and their wild swings tell us that within these serene-looking clouds, the birth of stars is a process of terrifying and chaotic violence. Violent flares and cosmic lasers are not the only way these clouds speak to us. Sometimes their language is a faint, steady whisper in a part of the spectrum we have only just begun to hear. Within the Great Orion Molecular Cloud Complex, a stellar nursery visible to the naked eye as the sword of the hunter, astronomers have tuned their instruments to the submillimeter waves, the domain between infrared light and radio waves. Here they listen for the faint signatures of complex molecules, the building blocks of life itself. And in this specific region known as Orion A, they have heard something that should not be there. It is a set of very narrow, specific frequencies of light being emitted, like a series of perfectly tuned musical notes. The problem is, these notes do not match the known vibrational song of any molecule we have ever catalogued, either on Earth or in space. It is as if you were listening to a symphony and heard a single, pure tone from an instrument you have never seen before. This presents a profound puzzle with three possible explanations, each more intriguing than the last. The first is that we have discovered a brand new, complex molecule floating in the depths of interstellar space, one our chemistry labs have never created. The second possibility is even more radical, that an entirely new type of chemical reaction is occurring in the extreme cold and low pressure of the cloud, a form of interstellar chemistry that defies our current models. The final, more sobering possibility is that this is an instrumental artifact, a ghost in the machine. But given the precision of modern telescopes, an unexplained artifact of this clarity would itself be a discovery of profound significance, pointing to a flaw in our understanding of the physics of light or detection. So we are left with a quiet, persistent signal from one of our closest celestial neighbors, a whisper that either heralds a new chapter in cosmic chemistry or asks us to question the very tools we use to listen. The quiet whispers of unknown molecules are not the only secrets these clouds hold. Sometimes the mystery is not in a signal's composition, but in its motion. In the sprawling, dusty lanes of the Rho-Ophiuchi cloud complex, a stellar nursery draped near the bright star Antares, radio telescopes detected a faint but persistent source. At first, it seemed unremarkable, just another speck of radio noise in a busy region. But when astronomers tracked its position over time, they noticed something deeply puzzling. This faint speck was moving, and its motion precisely matched the slow, grand rotation of the entire molecular cloud itself. It was co-rotating, locked in step with the swirling cradle of gas and dust around it. This behavior immediately ruled out most ordinary explanations. A distant galaxy or quasar far behind the cloud would not share this local motion. A normal star or even a young, hot protostar would have been visible in other wavelengths, shining with its own light. This source was radio quiet and dark, a ghost riding the cloud's rotation. So what is it if it's not a star? The leading suspect is a failed star, a brown dwarf. These are objects too massive to be planets, but not massive enough to ignite sustained nuclear fusion in their cores. They are cosmic embers, faint and cool, often detectable only by their heat in infrared or their subtle radio whispers. A brown dwarf deeply embedded within the Rho-Ophiuchi cloud could easily remain hidden at optical wavelengths, its faint radio emission betraying its presence as it moves with the cloud that birthed it. Yet, even this explanation feels incomplete. The signal's specific properties don't perfectly match known brown dwarf emissions, leaving room for more exotic possibilities. Could it be a strange, stable knot of magnetized plasma, a self-contained electrical storm somehow sustained within the cloud? Or perhaps a previously unknown stage of planetary formation, a super-Jupiter gathering mass in the dark, emitting faint radio waves from its powerful auroras. This co-rotating source is a shadow moving in lockstep with a cosmic dance, a reminder that even when we map the motion of an entire cloud, we may still have no idea what specific mysteries are waltzing within it. But what happens when a cloud is so dark and cold it seems to swallow the universe itself? Barnard 68 is not a glittering nursery, it is a cosmic shadow. This small, dense, and famously dark molecular cloud floats in front of the rich star fields of the constellation Ophiuchus, appearing as a perfect circle of nothingness, a hole punched in the Milky Way. Astronomers study it precisely because it is so opaque, using it as a natural screen to understand how starlight is absorbed and extinguished by interstellar dust. Yet when they turned radio telescopes toward Barnard 68 to study its most basic component, atomic hydrogen, they found an anomaly written in the language of cold. All across the galaxy, neutral hydrogen atoms emit a faint but steady radio whisper at a specific wavelength, 21 centimeters. By studying this signal, we can map the gas between the stars. In Barnard 68, researchers expected to see the hydrogen line, but they did not expect to see it like this. The absorption features were far deeper and more complex than any standard model of the cloud could explain. It was as if they were listening for a single voice in a quiet room and instead heard a profound, layered silence, a chorus of absences. This deep absorption suggests that within Barnard 68, there are pockets of hydrogen gas that are astonishingly cold, perhaps only a few degrees above absolute zero, and possibly denser than anticipated. This is a problem. In a cloud that is supposedly on the verge of collapsing to form new stars, we expect turbulence, slight warming, and movement. These ultra-cold, quiescent clumps do not fit the script. They behave more like fossils, pristine parcels of gas that have somehow avoided the stirring and heating that should precede star birth. One compelling theory is that these are remnants of the cloud's very formation, primordial knots of material that have survived unchanged for millions of years, nestled within the larger structure like ancient ice at the heart of a glacier. Their existence challenges our models of how molecular clouds evolve. If such cold, stable pockets are common, it means the journey from diffuse gas to newborn star is not a uniform process, but a patchwork one where pockets of the ancient universe can lie dormant, waiting in the dark. Barnard 68, that perfect circle of emptiness, may not be empty at all, but instead a deep freeze preserving the galaxy's oldest ingredients. While Barnard 68 whispers of ancient cold, another stellar nursery broadcasts a rhythm that feels almost musical. The Cat's Paw Nebula, officially known as NGC 6334, is a sprawling cloud of crimson gas and dust where massive stars are igniting in violent clusters. Within this chaotic forge of light and heat, radio telescopes picked up a series of faint, repeating pulses. At first, such periodic emission might suggest a rotating neutron star, a pulsar, sweeping its beam across our line of sight like a cosmic lighthouse. But the pattern from the cat's paw was different and deeply strange. The pulses did not arrive with the simple, steady beat of a clock. Instead, they occurred at precise harmonic intervals, their timing related to each other like the notes in a chord. One pulse, then another exactly twice as fast, then another 3 times the base frequency, a structured sequence of peaks in the radio data. This is highly unusual in nature. Astrophysical processes, especially the violent ones in stellar nurseries, tend to be messy and stochastic, driven by turbulence and explosive chaos. They do not typically produce clean, mathematical harmonics. It is the difference between the random crashes of thunder in a storm and the deliberate, tuned notes of a piano. For a brief and exciting moment, this harmonic pattern sparked discussion about a source that was structured, perhaps even engineered. Could it be a natural maser, but one operating under conditions so perfect it acts like a cosmic tuning fork? Or something more exotic, like vibrations resonating through a vast magnetized filament of gas, plucked like a string by a passing shock wave? The leading natural explanation points to a phenomenon called a beat frequency, where 2 or more independent pulsars with very close rotation rates create an interference pattern that appears harmonic to our instruments. Yet finding multiple pulsars perfectly aligned and timed within a single, chaotic nebula is itself a remarkable and unlikely cosmic coincidence. The harmonic pulses from the Cat's Paw Nebula remain an elegant mystery, a fleeting suggestion of order emerging from the heart of stellar chaos, a rhythm that hints at a universe capable of composing its own subtle, mathematical music. The idea of cosmic music gives way to a more visual, yet equally baffling phenomenon witnessed in the dark heart of another cloud. In the constellation Ophiuchus, a long, sinuous shadow stretches across the starry backdrop known as the Pipe Nebula. Its dark lanes are so thick with dust they blot out the light of stars behind them, creating one of the most recognizable silhouettes in the night sky. But when astronomers peer into these lanes not with visible light, but with infrared eyes sensitive to heat, they do not see a static darkness. Instead, they witness a subtle, chaotic dance of light. Specific, isolated knots within the cloud exhibit unexplained infrared flickering. These are not the predictable, rhythmic pulses of a variable star, nor the violent flares from a young star's accretion disk. This flickering is erratic, rapid, and localized to tiny patches of cold dust. It is as if someone were walking through a pitch-black cavern with a dying flashlight, intermittently pointing it at different walls for just a fraction of a second. So what could possibly be causing these sudden, transient flashes of heat in the deepest, coldest parts of a cloud? One compelling theory points to the dust grains themselves. In these frigid environments, dust grains can accumulate icy mantles of simple molecules. If a tiny, energetic particle from deep space, a cosmic ray, were to slam into one of these icy grains, it could deposit a sudden burst of energy, causing a minuscule, localized flash of infrared light as the grain momentarily heats up and then rapidly cools back down in the surrounding void. Another possibility involves shadowy dynamics on a larger scale. Dense, cold clumps within the cloud could be slowly collapsing under their own gravity, and as they compress, they heat up internally in fits and starts, creating these flickering hotspots. Yet the observed patterns don't perfectly match these models. The flickering seems too random, too brief. This leaves the door open for truly unknown transient events, perhaps magnetic reconnection events within the cloud's faint magnetic fields, snapping and releasing pent-up energy directly into the dust, or the fleeting passage of a previously undetectable, cold planetary mass object casting a thermal shadow as it drifts through. The Pipe Nebula's flickering is a silent, heat-based Morse code we are just beginning to see, a reminder that even in the darkest, most seemingly inert places, the universe is never truly still. This subtle flickering of heat is a clue that the interiors of these clouds are far from simple, and sometimes the clues are not in the light's brightness, but in its very orientation. Far from the Pipe Nebula, another stellar nursery drifts through our galactic arm, its shape so reminiscent of the American state that it earned the name the California Molecular Cloud. This vast, faint structure glows with the dim light of stars being born, and astronomers study it by analyzing not just the light's intensity, but its polarization, the specific direction its waves are vibrating. In the chaotic environment of a molecular cloud, dust grains are thought to align themselves with the local magnetic fields like countless tiny compass needles. The light passing through this dust becomes polarized, its vibrations lining up in a way that should, in theory, paint a map of the cloud's internal magnetic field. But when researchers created this map for the California cloud, they found a pattern that made no sense. Instead of showing the expected tangled, messy web of magnetic lines, twisted by the cloud's turbulent motions, the polarization data revealed something startlingly organized. Across enormous scales, much larger than any single star-forming clump, the polarization vectors showed a high degree of coherence. It was as if the entire cloud, hundreds of light-years across, was threaded by a surprisingly uniform magnetic field, a vast and orderly grid imposed upon the chaos. This defies our standard models. The turbulent gas motions within a cloud should scramble and distort magnetic fields on these scales, not preserve such clean, large-scale order. So what force is holding this magnetic tapestry so straight? One possibility is that we are witnessing the ghostly influence of an external, unseen power. The cloud might be embedded within a much larger, more powerful galactic magnetic field, one so strong and orderly that it overrides the cloud's internal turbulence, forcing the entire structure to align like iron filings on a magnet. Another, more intriguing idea is that the cloud's own history is the key. Perhaps the California cloud formed not from a chaotic collapse, but from a much more orderly process, like the slow compression of gas along a pre-existing, smooth magnetic field line in the galaxy. This would imprint a coherent magnetic signature from the very beginning, one that has persisted despite the cloud's evolution. There is also the faint, speculative possibility that we are seeing the aftermath of a past event, a shock wave from a nearby supernova that swept through the cloud eons ago, combing its magnetic field into temporary uniformity. Whatever the cause, this polarization anomaly is a silent testament to a hidden architecture. It tells us that the forces shaping these stellar nurseries are not just local and chaotic, but can be influenced by the grand, orderly currents of the galaxy itself, weaving invisible threads of magnetic order through the apparent darkness. That hidden magnetic architecture may provide a scaffold for creation, but it does little to explain the strange chemistry unfolding on a molecular level within the clouds. Deep within two separate stellar nurseries, the Perseus Molecular Cloud and the Chameleon Eye Cloud, astronomers have stumbled upon a chemical paradox that challenges our understanding of interstellar environments. The culprit is a simple molecule, or rather an ion known as CH+, a combination of one carbon atom and one hydrogen atom that carries a positive charge. In the cold, diffuse gas of a molecular cloud, CH+ should be incredibly fragile and short-lived. It is highly reactive, meaning it should quickly collide with other particles, especially free electrons, and be destroyed almost as soon as it forms. Its presence in any significant amount is a red flag, a sign of violent or unusual activity. Yet in both Perseus and Chameleon Eye, observations reveal a startling and persistent overabundance of this ephemeral molecule. It is as if you walked into a quiet, freezing library and found dozens of lit matches, each burning steadily without consuming themselves. How can something so fragile exist in such high concentrations in these cold places? The leading theory points to zones of intense turbulence and dissipation. Imagine the chaotic winds inside a storm cloud, where air masses shear against each other, creating pockets of violent friction. In a molecular cloud, similar turbulent motions, often driven by newborn stars or colliding gas streams, can create microscopic regions where the gas is suddenly and violently heated. In these brief hot pockets, the normal chemical rules are suspended. Carbon and hydrogen can slam together with enough energy to form CH+ before the surrounding cold snuffs the reaction out. The molecule is then rapidly ejected into the cooler surroundings, where we detect it before it ultimately meets its doom. This process, called turbulent dissipation, is like a cosmic spark plug, igniting chemistry in fleeting bursts. But the mystery deepens with the specific distribution. In these clouds, the CH+ is not spread evenly, nor is it concentrated solely near the obvious energetic sources like young stars. Instead, it appears in specific filaments and layers, tracing a map of hidden energy channels within the cloud. This pattern suggests the driving force might not be starlight, but something more subtle and pervasive, like waves of energy cascading through the cloud's magnetic fields or shock waves from events we have not yet identified. The twin enigmas of Perseus and Chameleon Eye tell us that these nurseries are not just passively cooking stars. They are alchemical forges where unseen forces stir the pot in ways we are only beginning to sense, creating and sustaining molecules that, by all rights, should not be there at all. The delicate chemistry of fragile molecules is one thing, but the Lupus 3 cloud presents us with an object that seems to defy the very categories of cosmic objects. This stellar nursery, a region actively birthing new stars, holds a secret that is not about light, but about its profound absence. Astronomers scanning Lupus 3 with radio telescopes found a compact, bright source. It was unremarkable at first glance, just another point of radio emission in a busy region. The mystery began when they tried to find its counterpart in other parts of the spectrum. They looked with optical telescopes, seeing nothing but darkness. They turned to infrared instruments, searching for the telltale warmth of a forming star or a failed brown dwarf. Again, they found nothing. This object was a radio beacon shining from a place of utter visual and thermal darkness. It was not just hiding, it was fundamentally cold. This presents a monumental classification problem. A typical young protostar, still swaddled in its natal cocoon of dust, would be invisible in optical light, but it would glow brightly in the infrared as its gravitational collapse generates heat. A brown dwarf, too cool for fusion, would still emit a detectable infrared warmth from its formation. This lupus source emits neither. It is radio loud and thermally silent. So what could possibly generate strong radio waves without producing any significant heat? The leading hypothesis points to an object in a state of extreme infancy or failure. It could be a so-called first hydrostatic core, a very brief stage in star formation that occurs just before a true protostar ignites. In this fleeting moment, a collapsing ball of gas becomes dense enough to be opaque, trapping its gravitational energy and beginning to warm up, but it is not yet hot enough to glow in the infrared. The violent motions and magnetic fields during this collapse could, in theory, generate the radio emission we see. Alternatively, it might be a pre-brown dwarf, a lump of gas that gathered almost but not quite enough mass to become even a failed star. This object would be so cold and dense, its only signature might be the faint crackle of radio waves generated by powerful auroras in its atmosphere, driven by a magnetic field interacting with infalling material. There is even a more exotic possibility that we are seeing a free-floating planetary mass object with an unexpectedly powerful magnetosphere, a rogue world emitting like a miniature pulsar. The cold radio source in Lupus 3 is a cosmic contradiction, a bright signal from what should be a dark and frozen place, forcing us to question where the line truly lies between a star that never was and a planet born from the void. These cold contradictions in Lupus 3 are not the only way dust reveals its secrets, for sometimes the dust itself seems to glow with a light we cannot fully explain. Our next two mysteries are connected by a faint, pervasive whisper across the microwave sky, a phenomenon astronomers call anomalous microwave emission. This is not the brilliant light of stars, but a subtle, enigmatic glow detected from specific, dusty regions of our galaxy. Two of the most telling sources are found in very different nurseries, the sprawling Rho Ophiuchi cloud complex and a small, in-Chi blotch known as LDN 1622, the Linz Dark Nebula. In both places, telescopes have mapped a faint microwave signal that stubbornly refuses to match the expected emissions from any known atom or molecule. For years, its origin was a total mystery, a ghost in the machine of the cosmos. The leading theory, which has gained significant traction, points to the smallest actors on the cosmic stage spinning nanodust. Imagine a grain of interstellar dust but shattered into a billion pieces, each fragment no larger than a single molecule. These are nanoparticles, likely made of carbon or other hardy materials. When such a tiny grain is struck by a single ultraviolet photon from a nearby star, it doesn't just heat up evenly, it can be sent into a frantic, high-speed spin, like a pinwheel caught in a sudden gust. A spinning electric dipole, no matter how minuscule, emits radiation. For these hyper-rotating nanoparticles, that radiation falls precisely in the microwave band, producing the faint, diffuse glow we detect. It is a beautiful and elegant explanation, the universe making light from the frantic dance of the smallest motes of dust. Yet for all its elegance, it remains a theory in search of a smoking gun. The major puzzle is the definitive carrier. While we suspect these spinning nanograins are responsible, we have not yet identified the specific molecule or type of particle that creates the exact signature observed. Is it a specific form of carbon, like tiny diamonds or sheets of graphene tumbling in space? Could it be complex organic molecules, the very precursors to life, spinning in the void? Every time we think we have a candidate, its predicted emission spectrum doesn't quite match the clean, broad signal from clouds like Rho Ophiuchi and LDN 1622. This represents a profound gap in our understanding of interstellar physics. We are mapping a glow that constitutes a significant part of the galaxy's microwave background, a cosmic hum we can hear but cannot yet name. It means that within these dark clouds, a population of particles we have never directly seen is performing a universe-shaping dance, their collective spin writing a message in microwaves that we are still learning how to read. That faint microwave hum from spinning dust is a testament to hidden, small-scale chaos, but the universe can also unleash violence on a far grander and more sudden scale. From the heart of the Monoceros molecular cloud, a sprawling stellar nursery in the constellation of the Unicorn, astronomers witnessed a different kind of signal altogether, one written not in microwaves or radio waves but in the searing language of X-rays. It was a transient flash, an explosion of high-energy photons that appeared, peaked, and vanished within a matter of hours. On its own, a brief X-ray flare in a star-forming region might not raise alarms. Young stars are notorious for their violent tantrums. But this event was different. The intensity was staggering, orders of magnitude more powerful than any typical stellar flare. Yet it was also strangely contained, pinpointed to a specific, seemingly quiet knot of gas within the giant cloud. This created a profound paradox. If the flash was caused by something cataclysmic and distant, like a gamma ray burst from a dying star in another galaxy, its signal would have been far more diffuse and would have left an afterglow across other wavelengths. This was a localized detonation. Conversely, if it was a local event from a flaring young star within the cloud, the energy required would be implausible, like a firecracker producing the force of a nuclear bomb. So what triggered this impossible explosion in the dark? The leading theories all involve hidden, exotic actors within the cloud's dusty vault. One compelling idea points to the sudden, catastrophic destruction of a small, dense object. Imagine a white dwarf or a neutron star, the remnant core of a dead sun, drifting through the cloud. If it were to pass too close to a massive, hidden gas clump or even another compact object, the immense gravitational tides could literally tear it apart in a single, violent episode. The infalling debris, heated to millions of degrees, would then unleash a torrent of X-rays as it was consumed. Another possibility is a magnetic monster awakening. Certain types of neutron stars, known as magnetars, possess magnetic fields so powerful they can crack the star's crust, releasing immense bursts of energy. A magnetar deeply embedded within the cloud, perhaps born in a previous, unseen supernova, could have experienced such a starquake, firing a focused beam of X-rays directly at us. There is also the tantalizing, though less likely, scenario of an intermediate mass black hole, a ghostly predator of hundreds of solar masses lurking in the cloud. A passing star or gas cloud ripped apart by its gravity could produce just such a brief, intense flash. The transient X-ray flash from Monoceros is a signature of sudden, apocalyptic violence in a place we assumed was only about slow, steady birth. It forces us to ask what else might be dying or being destroyed in the dark nurseries we think we understand. The X-ray flash from Monoceros was a violent, singular shout, but some of the most profound interstellar signals are not shouts at all, but entire conversations written in a language of molecules. Our next two mysteries are spectral forests, dense and bewildering thickets of chemical lines detected in the cold dark. The first lies in the most chaotic place in our galaxy, the galactic center. There, a massive, turbulent cloud known as Sagittarius B2 churns near the supermassive black hole. When radio astronomers pointed their telescopes at this maelstrom, they were stunned. The spectrum, which should have shown a few clear lines from common molecules, was instead a jungle. Hundreds, then thousands of sharp, specific emission lines crowded together, an entire forest of chemical signatures. Each line is the unique fingerprint of a molecule vibrating or rotating in space. This forest revealed a staggering zoo of complex organic molecules, many with structures resembling the precursors to amino acids and sugars, the very building blocks of life. The sheer abundance and complexity were the shock. Sagittarius B2 is bathed in intense radiation and shaken by powerful shockwaves from nearby stellar explosions. This environment was thought to be too violent, too destructive for delicate, complex chemistry to thrive. It should tear molecules apart, not build them up. Yet the forest says otherwise. Somehow, in the midst of this galactic chaos, an incredibly efficient and rapid chemical factory is operating, assembling these intricate molecules in the gas phase or on the surfaces of dust grains at a rate that defies our models. The implication is staggering. The most hostile place in our galaxy might also be one of its most prolific chemical laboratories, churning out the raw ingredients for life against all odds. The second forest is perhaps even more puzzling because it appears in a place of profound quiet. Far from the galactic center, high above the crowded plain of the Milky Way, drifts a small, isolated, and seemingly simple cloud. These high-latitude clouds are often pristine, cold, and diffuse, thought to be chemically immature. Yet when astronomers examined one such cloud, they found a spectral forest nearly as rich as the one in Sagittarius B2. This was utterly unexpected. Without the intense radiation fields, without the shock waves from supernova, without the dense crowding of stars, what force could possibly drive the creation of such a complex molecular menagerie? The energy to build these molecules has to come from somewhere. In this quiet cloud, the usual suspects are absent. This forces a radical reconsideration. Perhaps the seeds of complex chemistry are far more widespread and hardy than we ever imagined. Maybe the basic processes that link simple atoms into complex organics can occur in the cold, dark quiet, powered only by the faint glow of cosmic rays or the slow, cold chemistry on dust grain surfaces over millions of years. If that is true, then the raw materials for life are not special products of violent places, but could be a common, almost inevitable byproduct of the interstellar medium itself. These two forests, one from a galactic maelstrom and one from a cosmic backwater, present a unified mystery. They tell us that our understanding of interstellar chemistry is fundamentally incomplete. A hidden pathway, a set of chemical reactions we have not yet discovered, must be operating across the galaxy, weaving complexity from simplicity in both the loudest and the quietest corners of space. The universe appears to be pre-programmed with a drive toward chemical complexity, and these unexplained forests are its most eloquent and cryptic testimony. While spectral forests reveal a universe rich with chemical complexity, a different kind of signal once returned from a cloud, not with a whisper of molecules, but with the stark, deliberate echo of a human shout. The target was one of the most iconic dark patches in the night sky, the Coalsack Nebula, a vast and inky void near the Southern Cross that appears as a hole in the Milky Way. In the 1960s, during the early, ambitious days of radio astronomy, a team of Australian researchers performed a bold and controversial experiment. They aimed a powerful, focused radar beam, a concentrated burst of human-made radio energy, directly at the heart of the Coalsack. They were not expecting to communicate with anything, of course. Their goal was purely scientific, to probe the physical properties of the nebula's dust by analyzing how the signal scattered. What they recorded, however, defied those simple expectations. After the pulse was sent racing across the light years, the telescope's sensitive receivers picked up a faint but unmistakable echo. This in itself was not shocking. Dust scatters radar all the time. The shock was in the echo's character. Instead of being a diffuse, messy return, the signal that came back showed a surprising degree of coherence. It retained a clean, structured form, closely mirroring the original pulse. Even more puzzling was the time delay. Based on the known distance to the Coalsack, any echo from simple reflection off its diffuse front edge should have arrived with a specific timing. The echo they detected came back slightly too soon, as if it had reflected not off the cloud's outer boundary, but from something deeper within its structure. This combination of coherence and timing created a profound mystery. A cloud of interstellar dust and gas, no matter how thick, is an incredibly diffuse medium. A radar beam passing through it should be scattered in all directions by countless individual grains, its signal utterly shredded and returned as a faint, incoherent haze. A coherent echo, one that preserves the pulse's shape, implies a mirror-like reflection from a smooth, continuous surface, something completely alien to a tenuous molecular cloud. So what inside the coal sack could have acted like a mirror? The immediate and most sensational interpretation was that the echo came from a solid object, a vast, dark structure hidden within the nebula. This sparked wild speculation, though not of an artificial nature, but of a previously unimagined astronomical one. Could there be a colossal, cold sheet of material, a dark planetary nebula or a fragment of a shattered star lurking unseen within the dark cloud? The scientific community, however, remained deeply skeptical. The experiment was difficult to repeat, and alternative explanations were sought. Perhaps the echo was not from the coal sack at all, but a terrestrial interference or a reflection from a much closer object in our own solar system, like a passing asteroid or a dense plasma cloud in Earth's magnetosphere. Yet, the researchers argued their data ruled out these local sources. Another, more subtle natural explanation emerged involving the cloud's internal structure. If the coal sack contained unusually dense, sharp-edged clumps of gas with steep density gradients, these could, in theory, act as partial reflectors. A chance alignment of several such clumps along the beam's path might conspire to send a faint, coherent glint back toward Earth. This remains the accepted, if unsatisfying, explanation for most astronomers. But the controversy never fully died. The coal sack echo stands as a unique and unresolved anomaly, a moment where our own active probe of the cosmos returned an answer that felt too precise, too clean, for the fuzzy, chaotic reality of a dark nebula. It is a reminder that when we actively reach out and touch these clouds, they might just touch back in a way we cannot yet explain. That fleeting, coherent echo from the coal sack speaks to the transient nature of signals from these clouds, a theme that becomes even more stark in the chemical realm. In the delicate wings of the Cocoon Nebula, a beautiful stellar nursery catalogued as IC5146, astronomers witnessed a molecular disappearing act that defies all expectations. They were studying the cloud's chemical makeup, using its spectrum like a barcode to identify the molecules present. One particular scan revealed a strong, clear line from a known carbon chain molecule, a relatively complex structure built from a backbone of carbon atoms. These molecules are considered the heavy hydrocarbons of space, and their presence is a key indicator of active chemistry. The detection was logged, a normal part of mapping the nebula's inventory. But when researchers pointed their telescopes at the exact same patch of cloud just 1 year later, something was profoundly wrong. That specific, unmistakable spectral line was gone. It had not weakened or shifted, it had vanished completely, as if the molecule itself had been erased from that region of space. This was not a case of instrument error or bad data. It was a real and dramatic change in the cloud's composition on a timescale that is, in cosmic terms, instantaneous. Molecular clouds are supposed to be slow, patient places where chemical changes unfold over hundreds of thousands of years. For a complex molecule to appear and then be utterly scrubbed from a large volume of gas in a single year is like watching a forest grow and be clear-cut in the span of a minute. So what catastrophic event could purge a molecule so completely? The leading theory points to a sudden and violent influx of energy washing through that specific part of the Cocoon Nebula. Imagine a shockwave, perhaps from a distant supernova or a powerful stellar flare from a newborn star hidden deeper in the cloud, finally reaching this pocket of gas. When this wall of energy slams into the delicate carbon chain molecules, it doesn't just break them apart, it shatters them into their constituent atoms and ionizes them, fundamentally transforming the chemistry of the region. The molecules aren't hiding, they are annihilated. Alternatively, the event might not be destructive but transformative. The surge of energy could have provided the activation needed for those carbon chain molecules to rapidly engage in new, previously impossible reactions, linking up with other atoms to form entirely different, more complex species. In this scenario, the molecule didn't vanish, it evolved, leaving its old spectral signature behind as it became part of something new. This vanishing line is a ghost in the chemical record, a direct observation of the violent and mercurial nature of these nurseries. It tells us that the cloud's chemistry is not a static painting, but a dynamic and sometimes explosive film, where entire chapters of molecular history can be written and erased in the blink of a cosmic eye. The chemical vanishing act in the Cocoon Nebula reveals a cosmos in fast forward, but some changes are not erasures, they are strange and persistent drifts. From the high-latitude Cepheus flare clouds, a collection of dark, isolated nebulae far from the galactic plane, astronomers once detected a signal of almost painful specificity. It was a narrowband radio emission, a signal so finely tuned it seemed to whisper of a precise natural process or something more, but this whisper was not still. Over months and years of observation, its frequency slowly, inexorably drifted. It was as if a radio station were gradually turning its dial, shifting its broadcast ever so slightly away from its original channel. This slow drift is the heart of the mystery. Natural cosmic radio sources can change in intensity, they can flare and fade, but their fundamental frequency, the note at which they sing, is typically locked to a specific atomic or molecular transition and should be stable across the universe. A drifting frequency implies a physical change in the source itself. One possibility is a Doppler shift caused by the source moving toward or away from us at an accelerating rate. But the drift was too smooth, too consistent, and the required acceleration for an object embedded in a quiet cloud seemed unnatural. Another, more compelling idea involves a changing environment around the source. Imagine a powerful natural maser, its beam generated in a dense knot of gas. If that knot is slowly collapsing or being compressed by an external force, the increased density and pressure could subtly alter the quantum energy levels of the molecules inside, shifting the frequency of the light they emit. This would make the signal a direct barometer of a hidden, ongoing collapse. Yet no such protostellar core or obvious compressive force was found at the location. The Cepheus flare signal remains a spectral fingerprint slowly smudging across time, a change we can measure but whose cause remains just out of view. If that signal is a slow, deliberate slide, the next is a series of sudden, unexplained shouts. Within the NGC 2071 reflection nebula, a stellar nursery in Orion's sword, powerful water vapor masers flare like beacons. These are not the methanol masers of W30H, but jets of water molecules amplified to incredible intensities, often associated with the violent outflows from newborn stars. The puzzle in NGC 2071 is not their existence but their timing. On multiple occasions, specific water maser features have undergone sudden, dramatic intensification, spiking in brightness by orders of magnitude in a matter of days. The baffling part is that these spikes do not correlate with any observed increase in activity from the young stars thought to power them. No X-ray flares, no brightening in infrared, no increase in stellar winds. It is as if the engines of a power plant were humming along steadily, while a single light bulb in a distant warehouse suddenly blazes with the intensity of the sun. So what is flipping the switch? The leading hypothesis points to a phenomenon called stimulated emission, where a passing wave of the right frequency can trigger a cascade of emission from already excited molecules. But what generates that initial triggering wave? It could be a shock wave from a micro-event deep within the cloud, a small clump of gas collapsing, or a magnetic reconnection event too faint for our telescopes to see directly. This event would send a ripple through the cloud, and wherever that ripple passes through a pocket of excited water molecules, it sets off a brilliant flash. These maser flares are therefore not the primary explosion, but the cosmic equivalent of tripwires glowing brightly where an invisible wave of energy has passed. They map a hidden landscape of minor upheavals, telling us that even in a seemingly stable nursery, the ground is constantly trembling with tiny, unseen quakes. Between the slow drift and the sudden flash lies a third type of variability, one that hints at a hidden, rhythmic heart. Deep within the dense Serpens cloud core, a nearby and active star-forming region, astronomers monitoring millimeter wave emissions witnessed a different pattern, quasi-periodic fluctuations. The light from certain dusty knots would rise and fall, not with the random chaos of turbulence, but with a rough, approximate periodicity. It was an irregular heartbeat, a pulse that was almost but not quite a clock. This quasi-periodicity is a tantalizing clue. Perfect periodicity in space often points to a rotating or orbiting object like a pulsar or an eclipsing binary star. But this signal was messy, its intervals varying, suggesting the underlying process is more complex. The most likely explanation lies in the dynamics of accretion. Picture a newborn star still hidden in its dusty womb, pulling material from a surrounding disk. This accretion is not a smooth flow, but a chaotic, clumpy process. Dense lumps of gas and dust in the disk spiral inward, hitting the stellar surface or the inner disk in bursts. Each impact would release a flash of energy, heating the surrounding dust and causing a brief brightening in millimeter waves. The spacing of these bursts would be roughly periodic, dictated by the orbital dynamics of the densest clumps in the disk, but never perfectly regular because of the inherent chaos of the environment. Another possibility involves a hidden binary star system still in its formation, with the two young stars orbiting each other within a shared envelope of dust. Their gravitational dance could periodically stir and compress the dust between them, causing it to glow. The quasi-periodic signal from Serpens is the murmur of that cosmic construction site, the sound of building blocks falling into place in fits and starts. Together, these three variable signals, the drifting note, the sporadic flash, and the irregular pulse, form a trio of temporal mysteries. They prove that the greatest challenge in understanding these clouds is not just deciphering a single snapshot, but unraveling a movie where the plot keeps changing and the actors remain hidden behind a dusty curtain. While the Serpens cloud core murmurs with its own irregular rhythm, a much larger and more profound pattern of motion has been discovered, one that connects not just clumps within a single cloud, but entire stellar nurseries across our local galactic neighborhood. This is the mystery of the large-scale velocity coherence within the Good Belt. The Good Belt is not a single object, but a vast, tilted ring of bright stars, gas, and dust about 3,000 light-years across, with our solar system sitting near its center. It contains many of the most famous molecular clouds we've discussed, like Orion, Taurus, and Ophiuchus. For decades, astronomers mapped these clouds individually, studying their internal, turbulent motions. But when they stepped back and looked at the collective data, a startling pattern emerged. Across this enormous ring, spanning hundreds of light-years and encompassing clouds that appear physically separate, the gas exhibits a surprising degree of organized motion. Large sections of different clouds are moving together with coherent velocities that defy expectation. The problem is one of scale and time. Molecular clouds are seething cauldrons of turbulence. Internal motions from newborn stars, shockwaves, and magnetic forces should constantly scramble any orderly flow, like a spoon stirring cream into coffee. Over the millions of years these clouds have existed, that turbulence should have erased any large-scale, shared pattern of motion. The fact that we still see this coherence today means one of two things. Either the Good Belt system is much younger than we think, and the turbulence hasn't had time to fully randomize everything, or something is actively organizing and maintaining this motion on a colossal scale. What force could possibly choreograph the dance of gas across such vast distances? the leading hypothesis points to a galactic-scale event in our relatively recent past. Imagine a massive supernova explosion, or perhaps a series of them, occurring near the center of what would become the Good Belt. The blast wave from such an event would have expanded like a titanic bubble, sweeping up interstellar gas and dust, compressing it into the ring of clouds we see today. If this happened only a few tens of millions of years ago, a blink in cosmic time, the gas might still retain the coherent, expanding motion imparted by that initial shock wave. We would be living inside the still rippling aftermath of a local cataclysm, watching the clouds slowly drift apart with the fading momentum of that ancient explosion. Another, more subtle possibility involves the gravitational influence of an unseen structure. Our galaxy is not smooth. It is threaded with spiral arms and ripples in its disk of stars and gas. The Good Belt could be a local wrinkle caused by a passing density wave or a close encounter with a small satellite galaxy. This gravitational perturbation would have set the gas in motion, and that organized motion could persist if the driving force is still subtly present. There's even speculation about the collective gravitational effect of the belt's own massive stars and stellar associations, tugging on the gas in a coordinated way over time. Yet, each explanation faces challenges. A single explosive event seems almost too neat, and the timing is difficult to pin down. A persistent gravitational driver should leave other imprints on stellar motions that we haven't definitively found. This leaves the door open for something more fundamental, perhaps an unknown principle of how giant molecular clouds form and interact within the galactic ecology. The velocity coherence of the Good Belt is a ghostly signature written in the slow drift of nebulae, a hint that the clouds around us are not isolated islands, but connected chapters in a single, recent and violent story whose final page we have only just begun to read. This grand, choreographed motion of clouds sets the stage for a final, deeply personal mystery, one written not in radio waves or moving gas, but in the frozen heart of a single, silent object. Our final signal is not a broadcast but a fossil. Within the Ophiuchus molecular cloud complex, astronomers have focused on a specific, dense knot of gas and dust known as L1544. This is a prestellar core, a cold, dark cocoon that has not yet ignited a star. It is a snapshot of a solar system in its absolute infancy, a frozen vault where the raw ingredients for planets and perhaps life are quietly assembling. By studying the light that filters through this core, scientists can perform a form of cosmic chemistry, identifying the molecules present within its icy grains. Their focus fell on a molecule containing deuterium, a heavy isotope of hydrogen. In space, deuterium is rare, and its incorporation into molecules like heavy water or ammonia is a sensitive thermometer of past conditions. The colder and denser the environment when the molecule formed, the higher the ratio of deuterium to normal hydrogen tends to be. Standard models of interstellar chemistry predict a certain maximum for this ratio, based on the known conditions in molecular clouds over the last few billion years. But in core L1544, the measurements revealed something that should not be. The deuterium ratio in certain molecules was staggeringly high, far exceeding the predicted maximum. It was an isotopic anomaly so extreme, the models simply broke. This is not a case of slightly unusual chemistry, it is a fundamental mismatch. The ratio measured in that dark, starless cradle is more consistent with the chemistry of the very early universe over 13 billion years ago, when the cosmos was a simpler, more pristine place and deuterium was more abundant. The implication is profound and humbling. Somehow, deep within this unassuming knot in Ophiuchus, chemical processes that occurred in the first few 100 million years after the Big Bang have been preserved. The icy mantles coating the dust grains in L1544 may not be a recent frost, but a primordial ice, a relic from a time before our galaxy took its current shape. This core has acted as a perfect deep freeze, shielding these ancient molecular ices from the warming influence of starlight and the erasing power of cosmic rays for eons. It is a cosmic time capsule, and the deuterium is the seal. This impossible ratio forces us to reconsider the very history of our local interstellar material. It suggests that the cloud that formed our solar system might have contained similar pockets of ancient chemistry, and that the water in our oceans and the molecules in our bodies could carry within them a memory of the universe's first chemical whispers, delivered to a newborn Earth by comets and asteroids forged in a core just like this one. The final unexplained signal is therefore not about what is being created, but what has been perfectly, miraculously saved. That frozen vault of primordial chemistry in L1544 did not reveal itself easily. It took the most advanced ears and eyes humanity has ever built to hear its ancient whisper. To find these unexplained signals, we have had to construct a new kind of sense, one that can listen to the cold and see the dark. This technological hunt is a story of engineering on a staggering scale and quiet persistence in the face of cosmic noise. Our primary tool is the radio telescope, a giant ear turned to the sky. Modern arrays like the Atacama Large Millimeter/Submillimeter Array, ALMA, are not single dishes but orchestras of precision. Perched high in the Chilean desert, ALMA combines the signals from up to 66 individual antennas, working in concert to create a virtual telescope miles across. This gives it a resolution so sharp it could spot a golf ball on the moon. For molecular clouds, this means ALMA can do more than just detect a signal. It can map its precise origin within the swirling gas, pinpointing the exact dusty knot or filament where an anomalous molecule is forming or a strange flicker is occurring. It listens to the specific frequencies where molecules like methanol or those unknown spectral lines sing, building chemical maps of stellar nurseries with breathtaking detail. Then there is the 500-meter aperture spherical telescope FAST in China. Its colossal, bowl-shaped dish, nestled in a natural karst depression, is the most sensitive radio ear on the planet. Vast sheer collecting area allows it to hear the faintest whispers, the signals too weak for other telescopes to pick up. It is perfectly suited for the long, patient listening required to catch a one-time event like a new fast radio burst, or to detect the extremely faint radio emission from a cold, dark object like the one in Lupus 3. While ALMA provides the exquisite close-up, FAST provides the profound sensitivity, catching what others miss. But collecting the data is only the first step. The raw signal from these telescopes is a cacophony. To find the specific song of a single molecule, astronomers use a technique called spectral line surveys. Instead of tuning to one frequency, they scan across a wide range, capturing everything. The result is not a simple image, but a complex graph, a spectrum with thousands of peaks and valleys. Each peak is a spectral line, the fingerprint of a specific molecule vibrating or rotating in space. Finding an unexplained signal often means spotting a tiny, sharp peak that sits where no known fingerprint should be. It is like listening to a symphony of millions of instruments and identifying a single, pure note played by an instrument you have never seen before. This painstaking analysis turns the chaotic radio noise into a legible, if mysterious, chemical text, and there is simply too much data for any single team to analyze. This is where the global community enters the hunt through projects like SETI at home. While famously searching for signs of intelligence, the principle is the same for natural anomalies. Volunteers from around the world donate idle processing power on their personal computers to form a distributed supercomputer. This virtual machine sifts through mountains of radio telescope data, running algorithms that search for the subtle patterns that might indicate a repeating pulse, a narrowband signal, or an unusual burst that automated systems could overlook. It is a cosmic needle in a haystack search powered by the collective curiosity of millions. Every home computer running a screensaver becomes part of a vast, silent listening network, a testament to the human desire to find a signal in the noise. This technological trinity, the colossal telescopes, the precise spectral analysis, and the distributed power of human curiosity, forms our net cast into the cosmic dark. It is how we heard the harmonic pulses from the cat's paw and mapped the magnetic order in the California cloud. Yet for all this power, the greatest discoveries often come from recognizing that the signal we caught does not fit any of our carefully built models. The machines collect the data, but the human mind must confront the anomaly, the note in the spectrum that has no name, the pulse that echoes back too soon. Our tools are extending our senses into the void, but they are also revealing just how much we have yet to understand about the quiet, turbulent nurseries between the stars. The hunt for these signals inevitably leads us back to nature's own formidable creativity. Before we leap to conclusions about what we cannot explain, we must first grapple with the sheer, breathtaking weirdness of what we can. The universe is a master of generating phenomena that, to our limited perspective, can appear artificial or impossible. Three of the most powerful natural engines behind these interstellar mysteries are exotic pulsars, unstable masers, and the fundamental chaos of magnetized turbulence. Consider the humble pulsar, the spinning corpse of a massive star. We think of them as cosmic lighthouses emitting a steady, metronomic pulse as they rotate. But nature has produced varieties that defy this simple image. Magnetars, for instance, are pulsars with magnetic fields 1,000 trillion times stronger than Earth. These fields are so intense they can literally crack the star's solid crust, triggering starquakes that release sudden, colossal bursts of gamma rays and X-rays. A magnetar flare seen from within or behind a molecular cloud could easily be mistaken for a cataclysmic, one-time event, a transient flash with no obvious source. Then there are rotating radio transients, or RRTs. These are pulsars that only broadcast sporadically, sending out single, bright pulses that can be separated by hours or even days of silence. If one of these objects were embedded in a distant cloud, its infrequent, powerful blips would appear as utterly random, unexplained signals, appearing and vanishing without pattern. The pulsar family tree is full of such oddities, each capable of generating a signal that, in isolation, looks like a profound anomaly. Then we have masers, the natural lasers of space. We encountered them in the chaotic heart of W3OH, flaring unpredictably. The instability of these cosmic amplifiers is a key to many transient signals. A maser requires a precise, delicate balance. A population of molecules like water or methanol must be pumped to an excited state by an energy source such as starlight or a shock wave. The environment around a newborn star is anything but stable. A slight increase in the pumping radiation, a passing density wave, or a minor change in the magnetic field can push the maser past a threshold, causing its output to spike violently in a phenomenon called maser flares. These are not mere flickers. They can increase in brightness by factors of thousands in mere days. To an observer, this looks like a sudden, powerful signal appearing from a seemingly quiet patch of nebula. The maser itself is not the mystery, but its trigger often is. That triggering event, a hidden shockwave, a collapsing gas clump, remains the true unseen actor, its signature only revealed by the brilliant flash it ignites in the cloud's molecular gas. Underpinning both pulsar emissions and maser instabilities is the fundamental, chaotic force of magnetohydrodynamic turbulence. That is a complex term for a simple yet profound idea. The gas in molecular clouds is not still, it is a seething, magnetized fluid. Picture the most violent storm you can imagine, but scale it up to encompass light years, with magnetic fields acting as invisible ropes tangled within the gale. This turbulence is the engine of complexity. It can concentrate energy into tiny, intense regions, creating the hotspots that form fragile molecules like CH+. It can generate shock waves that travel through the cloud, compressing gas to trigger star formation or ignite maser flares. It can even, under the right conditions, accelerate particles to near light speeds, leading to bursts of synchrotron radiation, a type of emission often associated with black holes but possible in these turbulent plasmas. This chaos is not random noise. It has a structure with energy cascading from large scales down to small ones. Sometimes this cascade can produce transient, coherent structures, brief, self-organizing vortices or current sheets that might emit a short, clean signal before dissolving back into the turmoil. What we might catalogue as an unexplained narrowband pulse or a coherent echo could be the fleeting fingerprint of a temporary island of order within a sea of magnetized chaos. These natural explanations are not mundane. They are reminders that the universe operates on a plane of extremity we are only beginning to map. A pulsar's cracked crust, a maser on the edge of stability, a magnetic whirlpool light years across. These are not simple processes. They are nature operating at its most violently inventive. When we hear a strange signal from a dark cloud, the first question is not always what could it be, but rather, which of nature's incredible but known monsters is capable of this? Often, the answer lies in pushing our understanding of these known monsters to their absolute limits, to the point where the known physics bleeds into the unexplained, and the line between a solved mystery and a new one becomes beautifully, frustratingly thin. The known monsters of the cosmos provide a framework, but the most tantalizing signals push us to the very edge of physics itself, into a realm of speculation where the answers might rewrite the rules. When conventional explanations fail, scientists must, with rigorous caution, consider hypotheses that sound like science fiction. These are not wild guesses, but carefully reasoned ideas that extend our known physics into the extreme environments of interstellar clouds. One such frontier involves a state of matter so strange it defies intuition, the Bose-Einstein condensate. On Earth, we create these in labs by cooling certain gases to a fraction of a degree above absolute zero, where atoms lose their individuality and behave as a single quantum wave, a superatom. Could such a state exist naturally in the cold, dense hearts of molecular clouds? It is a staggering thought. If a sufficiently dense and cold clump of certain atoms or molecules could reach this QUINTUM Chinese letter, it would form a macroscopic quantum object potentially light years across. Such a condensate would have bizarre properties. It could, in theory, absorb energy in one part of the cloud and re-emit it coherently in another, almost instantly, acting as a quantum lens or amplifier. Could this explain a signal like the boomerang echo, where timing seems impossibly compressed? Or the harmonic pulses from the cat's paw, which hint at a system behaving as a single, tuned quantum entity? While the stability of such a vast condensate in a turbulent cloud is highly questionable, the mere possibility forces us to ask if the coldest places in the universe are hosting quantum phenomena on a scale we can barely conceive. Another shadowy candidate lurking in these discussions is the primordial black hole. Unlike stellar black holes born from dying stars, these are hypothetical remnants from the violent first moments after the Big Bang, and they could range in size from a speck of dust to a planet. A swarm of asteroid-mass primordial black holes drifting through a molecular cloud would be invisible to traditional telescopes, yet their gravitational influence would be profound. As they pass through the dense gas, they could create ripples of compression, triggering sudden bursts of star formation or heating pockets of gas to produce transient X-ray or radio flashes. They could even act as gravitational lenses, briefly focusing and distorting background radio waves, creating signals that appear, shift, and vanish. The controversial concept of dark matter adds another layer of potential mystery. We know it exists by its gravitational pull, but we have no idea what it is made of. Some theories suggest certain dark matter particles could accumulate in the gravitational wells of stars and planets. If these particles can interact with each other, they could annihilate, releasing bursts of energy. A molecular cloud with its deep gravitational potential could act as a dark matter reservoir. An annihilation event within a cloud's core could inject a sudden, powerful surge of energy into the gas, perhaps powering an unexplained maser flare or a transient X-ray burst like the one in Monoceros. The signal would be a side effect of the invisible universe briefly making contact with our own. And then, of course, there is the most controversial hypothesis of all, one that must be approached with immense skepticism yet cannot be dismissed outright: technosignatures. This is not about little green men, but the search for evidence of technology. If a signal exhibits properties that are extremely difficult, perhaps statistically impossible, to produce through any known natural process, we must consider an artificial origin as a last resort. A classic example is a narrowband signal with no sidebands, a pure tone that natural processes almost never create, or a signal that encodes information in a way that suggests a mathematical pattern like prime numbers. The harmonic pulses we discussed could, in an extreme interpretation, fit a pattern that seems engineered. The key is that a technosignature is not just a strange signal, it is a signal that carries the hallmarks of design and information. Scientists engaged in this search, like those with the SETI Institute, apply brutal filters to their data, eliminating 99.99% of signals as natural before even considering the remote possibility of technology. It is a hypothesis of absolute last resort, but to ignore it entirely would be to assume we are alone, a profound statement with no evidence. The purpose of exploring these exotic frontiers is not to prove aliens or quantum clouds, but to stretch the imagination of science. Each speculative hypothesis, from condensates to dark matter, serves as a stress test for our models. By asking if a Bose-Einstein condensate could cause an echo, we are forced to calculate the exact conditions needed, deepening our understanding of quantum mechanics in astrophysical environments. By considering primordial black holes, we refine our models of gravitational microlensing. These ideas are the stretching exercises of cosmology, pushing our thinking into uncomfortable new shapes so that when the next truly unexplained signal arrives, our minds are just a little more prepared, a little more open, to recognize a revolution if it whispers to us from the dark. These whispers from the dark are far more than cosmic curiosities. Each unexplained signal is a loose thread in the tapestry of our own existence, and pulling on it could unravel the entire story of how we came to be. To solve these mysteries is to decode the instruction manual for building stars, planets, and life itself. Consider star formation, the very engine of galactic evolution. Our textbooks describe a slow, gravitational collapse, but the signals tell a different tale. The violent X-ray flashes, the erratic maser flares, the quasi-periodic pulses, they all scream of a process driven by sudden, chaotic violence. If we can understand what triggers a transient X-ray burst inside a cloud like Monoceros, we learn about the hidden deaths and magnetic cataclysms that seed the nursery with shockwaves, compressing gas and kicking star birth into high gear. The harmonic pulses from the cat's paw and the coherent magnetic fields in the California cloud hint at a hidden order beneath the chaos, a scaffold that guides where and how stars assemble. By deciphering these signals, we move from a simple sketch of star birth to a dynamic movie, understanding the precise triggers and controls that determine whether a cloud gives birth to a solitary star like our Sun or a blazing cluster of giants. This leads directly to the origin of worlds and the chemistry that makes them alive. The spectral forests of Sagittarius B2 and the isolated cloud prove that complex organic molecules are being woven everywhere, in both the most violent and most quiet corners of the galaxy. The vanishing carbon chain line in the Cocoon Nebula shows this chemistry is not a slow simmer, but a rapid, explosive cookery that can be switched on and off. If we can identify the unknown lines in Orion or explain the impossible deuterium ratio in core L1544, we are essentially discovering new steps in the cosmic recipe for life's ingredients. Were the molecules in Earth's early oceans delivered by comets that formed in a core like L1544, carrying its primordial deuterium-rich ice? The answer is written in those anomalous signals. They are clues to whether the universe is inherently bio-friendly, predisposed to scatter the seeds of complexity wherever stars and planets form. Ultimately, these signals are our only direct probes into the true nature of the interstellar medium, the raw material of everything. It is not a uniform, passive fog. The boomerang echo and the Coalsack radar experiment suggest structures within it that can act like mirrors or lenses. The anomalous microwave emission from spinning nanodust reveals a population of particles so small they evade our sight, yet their collective glow shapes our view of the cosmos. The large-scale velocity coherence of the Good Belt paints a picture of recent local catastrophe, reminding us our solar system is evolving within a dynamic and event-driven environment, not a static one. Every unexplained signal forces us to redraw our map of this medium, adding new features like magnetic highways, quantum condensates, or dark matter knots. We are charting the ecosystem in which our solar system was born and now travels, so when we listen to a strange pulse or stare at a spectral line with no name, we are not just solving an abstract puzzle. We are reading our own deep history and glimpsing our possible future. We are asking if the forces that assembled our atoms and our world are common or a freakish accident. Each mystery solved tightens the connection between the cold, dark clouds and the warm, living planet we call home. The next signal we decipher might finally tell us whether, in the grand chemical laboratory of the galaxy, our existence is a likely paragraph or a single miraculous footnote. From the WOW signal's lonely shout to the frozen whisper of primordial ice, these 25 cosmic whispers form a single, undeniable truth. Interstellar space is not a silent void. It is a vibrant, chaotic, and deeply mysterious ecosystem. The dark clouds between the stars are not empty backdrops, but active characters in the story of the universe, broadcasting their secrets in a language we are only beginning to translate. Each unexplained signal, whether a fleeting X-ray flash or a drifting radio note, is a crack in the facade of our understanding, letting in a sliver of light from a reality far stranger than we imagined. They tell us that star birth is a violent, punctuated drama, that the chemistry of life may be written everywhere, and that the very fabric of space may be threaded with quantum oddities and hidden forces. This journey is not a catalogue of solved cases, but an open investigation. The greatest discoveries still lie ahead, waiting in the static between stations, in the next scan of a dark nebula, in the patient analysis of data from a telescope on a remote mountaintop. Our role in this story is not to be passive listeners, but active participants in a grand, collective act of curiosity. So the next time you look up at a dark patch in the Milky Way, know that you are not staring at nothing. You are gazing into a cosmic laboratory, a turbulent nursery, a vault of ancient chemistry. The universe is speaking in boomerang echoes and harmonic pulses, in spectral forests and vanishing lines. Stay curious, keep looking up, and follow the scientists, the engineers, and the volunteers around the world who are tuning their instruments, refining their models, and listening ever more closely, because the next great cosmic whisper could arrive at any moment, ready to rewrite everything we think we know.